Welcome to the course on fundamentals of MIMO wireless communication. Now we are undergoing the discussion on multipath propagation effects. Whatever we discussed in the previous lecture is one of the foundations on which the whole course is standing. So we'll take a little bit more deeper look into the expressions which we have developed towards the end of the last lecture. So what we discussed in the last lecture is the complex envelope of the received baseband signal, which can be represented in this form, where h t comma tau n is the product of the amplitude coefficient associated with the nth path, and the phase associated with the nth path, and we wrote it could be written as a convolution expression. So what we will now try to do is take a detailed look at how does this arise. So when we write that r tilde t is equal to n is equal to 1 to capital N h of t comma tau n s tilde t minus tau n, this we could also write as instead of having tau n written over there, we could easily write it as h n of t, because this is dependent on the nth path multiplied by s tilde t minus tau n. The n gets reflected in the phase where you have f c tau n. So tau is getting multiplied. In that case, we are suffixing n to indicate the nth path. If we expand this, we could write this as h 1 of t multiplied by s tilde t minus tau 1. That means signal which started at a time tau 1 units of time before the current time has come through the first path, which has a delay of tau 1, and there is a coefficient h 1 which includes the amplitude and the phase change associated with the first path, plus h 2, that means the coefficient associated with the second path, s tilde t minus tau 2, and so on, the generic being h n of t s tilde t minus tau n up to h capital N of t s tilde t minus tau capital N. So if we see this expression, we could pictorially write this expression as the signal s tilde t getting transmitted. There is some propagation delay, and after which we have s tilde t minus tau 1. Let us say the delay is tau 1. This is getting multiplied by the coefficient which is h 1 of t, and then the signal goes out. It gets added to s tilde t minus tau 2. That means this is delayed further to the another path. There is multiplication by a gain h 2 of t gets added to that, so on. S tilde t minus tau n gets multiplied by the gain h n of t, and so on up to s tilde t minus tau capital N, which gets multiplied by h n of t gets added, and what we get at the output is r tilde of t. So as if the signal after a delay is getting multiplied by one coefficient, further delayed multiplied by second coefficient, further delayed multiplied by third coefficient, and so on. So, we could set this as almost a finite impulse response filter or a transversal filter structure. So, we could write these expressions in a better way and state that we have R tilde t is equal to filtering of S tilde t with H t of n, which we have as H t comma tau n convolved with S tilde t, where we could write H t comma tau is equal to the sequence n equals 1 to capital N, H of t comma tau n, it's a convolution of H t comma tau times delta tau minus tau n, or in other words, what we have again pictorially, if this is the delay axis, we call this the delay axis and this is the gain axis. So, at a delay of tau 1, what we have is H 1, and remember it is a function of time. At a delay of tau 2, we have H of 2, which is also a function of time. At a delay of tau n, of course, they are in between, we have H n t and so on. Finally, at the last delay tau capital N, we have H n of t. So, that means this is the what we can say is H t comma tau represents the channel impulse response, because we are having a convolution of the channel impulse response with the signal to get the received baseband signal or the received complex envelope, and the H values represent the different coefficients of the impulse response or the filter taps, which themselves are function of time. What you may have encountered before is such a situation, that means such a filtering, linear transversal filters, where these coefficients were not varying with time. These were constant with time, and you had a linear time invariant system, but what we encounter here is a linear time variant system, and this is fundamentally because of the phase, which is a function of time, and that has happened because of the multipath propagation, where we have mobility involved as part of relative distance between the transmitter and receiver, or the points of reflection, or the surface on which the waves impinge. So, we could also look at this expression, that means R tilde t is equal to, if we look at this expression R tilde t, which we have been writing, is equal to sum over n H n of t multiplied by S tilde t minus tau n. What we could also say is that, as if we have the situation where the signal S tilde t, which is generated at a time t minus tau 1, let us say, and scaled by h 1 of t, right. That is what we are getting over here. If you see all this picture, generated at a time tau 1 before t, scaled by h 1 of t, is added. So, let us write that it is added to S tilde t generated at a time t minus tau 2 units scaled by h 2 of t and is added to. So, this generated tau 1 units of time ahead scaled by h 1 of t added to s tilde t generated at a time tau 2 units before scaled by h 2 t added to the others, and so on and so forth. It keeps on. We could write it as the one which is generated at tau n times before multiplied by h n added to, and it continues to t minus t n h n of t. So, what does it mean? It effectively means that s tilde t, which is the basic signal or the signal that is generated, is getting added to something. So, what we have is some signal generated at some earlier time scaled getting added to the same source, but generated at a different time. Now, these two signals, just consider a digital communication system where at certain time t 1, let a signal like this be generated, at another time t 2, let us say this signal is getting generated, at a time t 3 we might have a signal this generated, at a time t 4 it might be this generated, and so on, it goes on. So, what this statement tells us is that signal generated at time, let us say t 1 gets multiplied. So, this value gets multiplied by, let us say h 1, this gets added to the signal which is generated at time t 2, t 2 is equal to t minus tau 2, gets multiplied by h 2 plus the signal which got generated at time t 3 gets multiplied by h 3, and so on and so forth. So, clearly the received signal has multi path. These are due to the paths because they are equal to C n e to the power of j phi n h n, this we have already said, multipath, and since they are all getting added, as we see in this expression, they are all getting added, they are getting mixed up, we use the term multipath interference. So, what we have is signals from different delays scaled by appropriate path coefficients are getting added together and it is mixed up. So, what we can see is that a clean signal which we have drawn over here will not appear in the same way at the receiver. We could draw another picture and try to look at it, what would happen. Suppose I have a signal sequence which goes like this. So, at the receiver at this instant of time, what do I expect? What I expect is the signal which was transmitted here gets scaled by h 1 plus the signal which was transmitted here gets scaled by h 2 plus what was transmitted here gets scaled by h 3, and so on, and finally received over here. So, if I would have the received axis on time and let us say the received signal on this axis, we are never sure what is the value of the signal that we get. If there was no such multiplicative factor, for instance, if we did not have any such thing, suppose we had all of this as zeros and this as 1, we would have had only the delayed version of the original signal. That signal scaled by some arbitrary value added to another signal scaled by an arbitrary value, we would not be able to draw the signal that we get over here. So, the signal amplitude could be here and the next time instant signal amplitude could be anywhere. We are not sure where the signal amplitude will lie, because that would depend upon the coefficients h n, and there is a summation of all of these coefficients. So, we have a arbitrary sequence which comes at the receiver. Now, if we are able to understand this thoroughly, then when we build the receiver from this combination of signals, we would like to extract S tilde t, so that the signal which was originally transmitted is reconstructed at the receiver without any effect of the propagation channel. Now, let us go ahead a little bit further, and what we would assume is that these delays that we are suggesting over here are negligible compared to the symbol duration. So, what we mean is if the symbol duration is this much, if this is the symbol duration, the delays are very small, right. So, what we would have seen in this case, if you have to reconstruct the signal transmitted at a certain delay. So, basically there would be a delay, the signal generated, added to the replica of the signal, delayed, but this getting scaled by h1, this getting scaled by h2, again there is a delay scaled by h3, all of this added together. What we are now making the assumption is these delays are so small that they are negligible compared to the symbol duration, or in other words, if a transmitted sequence is this, I am drawing a random transmitted sequence which is probably different from the previous transmitted sequence. The delays are so small that the received signal would be hardly much delay amongst the paths. So, if this is the signal that has come through the first path, of course, we are not making assumption on the coefficients. What has come through the second path, what has come through the third path, and of course, there are associated scaling coefficients. So, this is what is the assumption that we are making at the receiver front. So, in other words, we are saying that this tau I minus tau j for I not equal to j is very small. In other words, when we are writing the coefficients, that means when we are writing the channel impulse response, we would look at this particular expression. So, what we could write is the h of t comma tau, which was equal to sum over h n of t delta tau minus tau n, n equals to 1 to capital N. Now, since we have written that let tau 1 is almost equal to tau 2 is almost equal to tau n is almost equal to tau capital N, and let that be equal to some tau cap, then we could write this as equal to h n of t multiplied by delta tau minus tau cap. So, what we have is effectively all these delays, they were different previously, now they are the same. So, what we are saying is, just try to use a previous picture. If I have it here, it is good. Yeah. So, we have this picture. So, previously, because of this expression delta, these delays, that means h 1 at tau 1, because of the delta function it is shifted at tau 1, because of the delta function h at 2 is shifted to tau 2, because of tau n it is shifted at tau n. Now, these tau n's are very close to each other. So, we will probably have h 2 over here, h 3 over here, h 4 over here, h 5 over here, h 6 over here. So, as if the delays are very close. So, what we mean pictorially is, in this only we could draw, is that the transmitter, so will not violate our earlier picture, receiver, signal propagates through path tau 1, signal propagates through path tau 2, signal propagates through path tau 3, signal propagates through path tau 4, and so on. All we make the assumption is that this propagation delay is negligibly small difference between them. There is negligible small difference in the delay. Now, this can happen if the transmitter and the receiver are at the two focal points of an ellipse. In that case, all the path lengths are exactly the same. So, we are not saying that they are exactly the same, but they are very, very close to each other. So, as if all the reflectors, scatterers, everything are located in such a way that the propagation delay is very, very similar. Now, this could give rise to the situation where phi 1 is equal to phi 2 is equal to phi 3 and so on, and that would destroy the whole structure. However, we remember the expression of phi n is contains f c times tau n, and there we have seen that a gap of a delta tau n is almost equal to 1 nanoseconds causes delta phi n to be changing by nearly 2 pi. So, we make the assumptions that although they are very close, that means these tau n's are not separable, but phi n's are still quite different. That is a very, very strong assumption that we make. So, with this what we have is this expression is this tau cap is common for all. So, therefore, we could add up everything and we need not have the summation sign anymore. So, what we could write this as h of t, because all h n have added up. Now, because these tau gaps have gone, previously they were at different delays. So, they were not getting added up, they were at separate gaps, but now since they have almost come to each other, very close to each other, we are as if they are at the same time location approximately. This is a model. So, this is an approximation. So, we are able to add them up and we are having a single effective h of t times delta tau minus tau cap. So, what does it affect in our diagram? In our diagram, these particular figures, all these tau n's are getting modified to the same value of tau. So, what we have now is s tilde t minus tau cap getting multiplied by h 1 of t is of course s tilde t coming, s tilde again look at this t minus tau cap, because the delays are the same, but getting multiplied with h 2 of t. Although the delays are same, still the coefficients are different. This is very, very important. So, we will have s tilde t minus tau cap for all, because delays are same, but we are going to have h n of t and we are going to have multiplication by h capital N of t, and they will all be added together and sent out. Now, since all these delays are same, we could draw this example as if there is s tilde t minus tau cap coming from the source and it is getting multiplied by a single h of t as we have drawn earlier, and it is going out to give r tilde t, or in other words we could write r tilde t is equal to h of t multiplied by s tilde t minus tau cap. Now, this is because we have g of t comma tau is equal to we have h of t comma tau is equal to h of t multiplied by delta tau minus tau cap. That means, there is a propagation delay corresponding to tau cap and there is a coefficient. Now, when we study filters, we study channel impulse response as well as the frequency transfer function. To study the frequency transfer function, we need to take the Fourier transform across the delay domain. So, that means we have to take the Fourier transform across this axis. So, if we take the Fourier transform across this axis, we could get h of t, because we are not taking Fourier transform in the t axis, we are taking Fourier transform across this axis. Let us put nu, which is equal to integration from 0 to tau max. So, by tau max we mean the maximum value or tau n in this expression. So, here tau max could be equal to tau n in our expression, and since it is continuous domain that we are doing now, it will be tau max. So, we could have h of t delta tau minus tau cap e to the power of minus j 2 pi f, sorry, we should have nu tau d tau. This would result in h of t, because this is not dependent on any such expression, and this integration would result in e to the power of minus j 2 pi nu tau cap, this whole function being shifted by the delta function. If you look at the amplitude of this, that is the mod of h of t comma nu, what you would get is the modulus of h of t, because this modulus is unity. So, what we see is that the amplitude response of this particular expression is not dependent on nu, because when we take the modulus, this is not dependent on nu, this is dependent on nu, whereas this is becoming unity. So, this is independent of the frequency, however, it varies with time. So, if we are plotting the frequency response, and let us say this is the nu axis, this is the gain axis, what we will get is across our interest of frequency zone, we are going to get a flat response. It is not dependent on frequency, it is the same value across different values in frequency. However, if we draw the time axis, what we will see is that this value is fluctuating with time. So, that means across time, across this whole set of bandwidth, the magnitude is remaining the same, there is no change in magnitude across the bandwidth. However, that same magnitude is fluctuating across time in as depicted in this figure. Now, since across the bandwidth there is no fluctuation in the amplitude, this is aptly known as frequency flat fading. Why this fading? Because there is time domain fluctuation. Why this flat? Because in the frequency domain there is flat. And why is it flat? As we have clearly seen, if we take the Fourier transform of this channel impulse response, we get a situation which is independent of frequency. If we take the amplitude of it, the reason being the channel impulse response is simply one delta function which is scaled by a value, or in other words, if we look at the channel impulse response, it is just one impulse. And if you remember, the Fourier transform of an impulse is flat across the entire range of frequencies. So, that is the final consequence that we have, that if this delays or this path differences is negligible relative to each other, we have all the paths arriving at the same time. In that case, the frequency selectivity of the channel is flat. That means, it is not fluctuating with frequency, but it is fluctuating with time. The important consequence of this is that if I have a signal which spans between the frequencies nu 1 and nu 2, in that case the entire bandwidth of the signal is not going to experience variation of gain. The entire bandwidth of the signal is going to experience the same value of the channel amplitude. However, that is going to fluctuate with time. In this course, we will use this model almost entirely. So, this is a very important part of the lecture, and I would recommend you to go through this as many times as possible so that you get an understanding of how we have arrived at the expression and what is the meaning of this frequency flat fading. Thank you.